Hey students, welcome to lecture number 4 of multiple zeta values and modular forms. So today I want to talk about section 1.4 where we talk about q-analogues of multiple zeta values. So first recall, last time we did section 1.3 and there we talked about modular forms and their basic properties and also talked about the relationship between the dimension of cusp forms and relations of double zeta values. And today we want to talk about the Fourier expansion of these Eisenstein series and see that these give some q-analogues of Riemann zeta values, and then we want to define their multiple versions, which we will denote here by this small g of some index k. And then we also want to talk about their algebraic structure in the lowest depth case, and similar to the formulas we obtained for these Riemann zeta values where we had the shuffle and the Staffel product, we will also give an analog for this q series small g. Okay, so first a little bit review from last time. So what was a modular form? A modular form of some integer weight k satisfied three conditions. So first it was an holomorphic functions. It was a holomorphic function in the upper half plane. So the complex upper half plane was just the set of all complex numbers with a positive imaginary part. And then it satisfies certain transformation properties. And we saw that there are two essential functional equations a modular form needs to satisfy. So one of them was that it needs to be one periodic, and the other one was that it satisfies this equation here. And this was needed to be true for all tau in the upper half plane. And then the third condition was that the modular form f has a Fourier expansion of this form, where this q is e to the 2 pi I tau. And the main point was that this sum here starts at 0. And another way to phrase this means that this f tau is bounded when the tau goes to I infinity, here for example on the imaginary axis, and then the value a0 here was exactly given by this limit here. Okay, and then as an example for a modular form, as a non-trivial example, we defined these Eisenstein series given by this double sum here. And this sum here converges when this k is strictly greater than 2, but we just defined this for even k greater or equal to 4, because we will define this for odd k's in a different way. And then this gave a modular form of weight k, and the Fourier expansion is given by this sum here, where the a0, the constant term, is given by the Riemann zeta value, and the other an are given by some multiple of these divisor sums. So clearly in this sum here, if you send q to 0, what you get back is the Riemann zeta value. But what we want to see today is we will consider the case when q goes to 1, and here I not just send q to 1, I also will multiply by some factor, and then we will also see that we will get back zeta k, and then we want to modify this thing here to get somehow not just the Riemann zeta value, but any multiple zeta value. And therefore this can be seen as a q-analog of this Riemann zeta value. So this is the first thing we want to talk about today. So what is a q-analog? So in general, a q-analog of some object is always an object depending on some variable q, and sending q to 1 gives back the original object. So one example is, for example, if we have a positive integer, then the q integer, which is usually denoted by mq, is given by this fraction here, 1 minus q to the m divided by 1 minus q. And if m is a positive integer, you can also write this as this sum here. And then clearly, if you send q to 1, this just gives back m, because then you have m copies of 1 there. So if we want to define a q-analog of multiple zeta value, so let me remind you of the definition here. So this is the definition of a multiple zeta value. And here in the definition we have some integers. So one naive way would be to say, well, we can replace this m by this q integer m, and then clearly q goes to 1 will give back the multiple zeta value. But one problem is, if you just replace, for example, this m1 here by this fraction here, then this as a q series, so if you divide 1 by this as a q series, will have a constant term. So you would have a 1 here plus something. So this wouldn't really give a well-defined q series. So what you need to do is you also need to put some factor q here in the numerator. And there are different ways to define q-analogues of multiple zeta value, and one common way is the following, which was independently studied by Bradley and Chow. So that's why I denote this by BZ here. So this is Bradley Chow. So this is the so-called Bradley-Chow model. And what they do is where they replace the integers here in the definition of multi-zetas by this q integer. And in the numerator they put a polynomial in q to the power m, where they put here as the exponent k1 minus 1 up to kr minus 1. And with this, one can check that if one now takes a limit, q goes to 1 of this beta q k, then of course in this case k needs to be admissible. And also every time in the following, if I write q goes to 1, what I mean is that q is an element in the unit disk and it goes to 1 on the real axis from the left. And with this, one can argue why it's allowed to interchange the limit and the summation here, and then sending q to 1 in this thing here. Here we will just get m1 to the k1 up to mr to the kr, so exactly this. And in the numerator, well, if you send q to 1 there, it's just 1. So this will give back just the multiple zeta value. And that's why this is an example of a q-analog of a multiple zeta value. But of course, you can also choose another polynomial here in the numerator, which we will do soon. And also, instead of choosing the q integers here, we will also remove this factor 1 minus q. And this is what I want to explain now, because this is what I want to call a so-called modified q-analog. And what do I mean by this? So let's say modified q-analog of some object f of weight k. So what I mean by this is that I have some q series, for example fq, which depends on some variable q, where q is again an element in the open unit disk. And modified q-analog, I mean that I first need to multiply by 1 minus q to the power k, and then send q to 1. And if this gives back f, then I call this fq a modified q-analog of f. So this modified just means that we do not include this factor 1 minus q in the definition of fq. Well, but why is this? Should we be interested in this object? Well, one example is that, for example, modular forms are modified q-analogues. So more precisely, if I have a modular form, so now usually in the definition we wrote this is f of tau, but we can also view it as a function of q. So by abuse of notation I will use these two notations, f of tau and f of q. And f of tau just means this is q is e to the 2 pi I tau, And if I have a modular form of weight k, then this modular form f is up to some power of pi, a modified q-analog of its constant term. Meaning, if I multiply this modular form by 1 minus q to the weight of this modular form, and then send q to 1, I will get back the constant term a0 times some factor in front, which is here 2 pi I to the power k. And so there are two ways to see this. So one way we will explain later. So every modular form of weight k can be written as a polynomial in g4 and g6. And then this statement just needs to be checked for g4 and g6. And this we will do in a second. But there's also a more direct way using the definition of modular form to show this property. So remember, if I have a modular form of weight k, then it satisfied this transformation property, that f of minus 1 over tau equals tau to the k f of tau. And then, on the other hand, because this q is e to the 2 pi I tau, oops, let this put here, this means this factor 1 minus q to the power k, if I write out the Taylor expansion of the exponential, then the constant term is 1, which I erase here, and then the next term is minus 2 pi I tau plus, and then, or minus, there are some more higher powers of tau, so here I could write plus O tau k. Oops. Let's do it like this. So this I raise to the power k. So this will give something like something to the power k plus, and then higher powers of tau. Okay. So now let's see why we get this limit here using these two things. So the limit q goes to 1 minus q to the k f of q. So remember, goes to 1. So here we are in the unit disk, and q goes to 1 means q goes here to 1, and this map q was a map from the upper half plane to the unit disk, and in the upper half plane this corresponds to tau going to 0 on the imaginary axis. So in other words, this is the same as tau goes to 0, and now we can use this here. So this is some 2 pi I to the power k f of tau plus the rest. The rest will vanish, as we will see in a second. And now we can use this transformation property here, because here we have f of tau times tau to the power k. So this is just, so using this thing there, we get, this is a limit, tau goes to 0, of 2 pi I to the power k f of minus 1 over tau plus dot dot dot. And here the rest, because here in these I have higher powers of tau, so here I have tau times some f, and this part will just vanish. So because this, if tau goes to 0 here, and I consider minus 1 over tau, this is just the same as taking the limit tau goes to I infinity, 2 pi I to the power k f of tau. But the value of a modular form when tau goes to I infinity is just a constant term. So this is just 2 pi to the power k, oops, a0. And this part here vanishes because here, well, it vanishes because we still have some factor of tau here, and this tau goes here to 0. Okay, so this is one way to prove this fact, and therefore every modular form is a modified q-analog of its constant term. So in other words, if you have the Fourier expansion of a modular form, but you forgot the constant term, then from the rest of the q expansion, if you know this is a modular form, you can get back the constant term by taking this limit here. Okay. So now, we want to introduce a q-analog, a modified q-analog of multiple zeta values, which we will denote by these small g. And so again, as I said in the beginning, we defined these Eisenstein series, which had this Fourier expansion here. And this definition we did for k greater or equal to 4 and even. But this Fourier expansion also makes sense for any k. And because of this factor 2 pi I to the power k we saw before, so if I would multiply this by 1 minus q to the power k, and then send q to 1, then I would get 2 pi I to the power k times the constant term. And since we want to get a q-analog of these zeta values, we will divide out the 2 pi I to the power k. And what we get is this gk. So again, this is just, we divide out this 2 pi I to the power k of this gk of tau. And due to this formula we did in the first lecture, this zeta value here for even k is just given by this. So if we divide out this 2 pi I to the power of the weight, we just get the Bernoulli number here as a constant term divided by some factorial. And the rest is just given by this here. And so this we define for any k greater or equal to 2. And this thing here is now what we want to call small g of just one number k. And so what is this? So we can rewrite this sum a little bit like this. So this gk is now this part here. So it's just given by this sum here. And the sum of divisors can be written like this, because if you consider now the coefficient of q to the n, then you take the sum of all divisors d to the power k minus 1, and this is exactly the definition of this sigma k minus 1. And here is just still the factorial. And now this can be written as this, where this pk is a polynomial with rational coefficients. And this is exactly defined by this equation here. Namely, one can show that this expression here, so in more general, this expression here, this can be just written as some rational function with some pole at x equals 1 of order k. And here we have a polynomial, and these polynomials are called Eulerian polynomials. So these guys here. And let me give you some examples. So for example, p1 of x is the same as p2 of x, which is just x. p3 of x is 1/2 x times x plus 1. And for example, p4 of x is 1/6 times x squared plus 4x plus 1, and so on. And maybe one comment, usually what people call Eulerian polynomials are just these factors here. So in our definition we have an additional factor x, and also we include these factorials. But so what do we want to do now is to show that this gk is actually now a modified q-analog of the Riemann zeta value. Well, which we actually already know for the even case, because this follows from the proposition we did before for modular forms. But for other case, we cannot really use this modularity property, but we can show this with elementary methods. So let us see what happens if we multiply this gk with 1 minus q to the k. So this is by definition not this, but this is this. Pk q to the m 1 minus q to the m to the power k. And now if you multiply this in here, what you see is that this part here is exactly 1 over the q integer m. So this is just pk q to the m divided by the q integer to the power k. And therefore, if you send this q goes to 1, and you can again argue why you can interchange the summation and taking the limit, then this is pk of 1, because here we send q to 1, so we get the value of this polynomial at 1, times, and here this just goes to m, so this is just the definition of the Riemann zeta value at k, so this is zeta of k. But now, so if we look, for example, in these examples of the Eulerian polynomials, what happens if I plug in 1? So in this case, if I plug in 1, it's just 1. P3 of 1 is 1 times 2 divided by 2, so this is also 1. And here if I plug in 1, then here I got 6 times 1 divided by 6 is 1. So in these cases, pk of 1 is 1. And what you will show in the exercises is that this is always the case, that pk of 1 is always 1, and therefore this here is just zeta of k. So this small gk is a modified q-analog of zeta k, because after multiplying with this 1 minus q to the k, sending q to 1, we get zeta k. And also what you see, which is quite obvious from the definition, is that pk at 0 is 0. So in other words, this gk makes sense for any integer k greater or equal to 1, because if k is 1, then we still have some factor here of q, so these guys will always be some formal q series with rational coefficients. Okay, so this is the definition of small g for one integer k. But what we want to do now is define the multiple version, and the idea is just to replace this single sum here by a multiple sum, by just taking the sum over ordered m's here, and then with the same argument as here, these guys will give, so the same argument as here, these will give modified q-analogues of multiple zeta values. And this is this definition. So for any index k, we define these g of this index, which we also write g of k1 up to kr, as an ordered sum. And here we take these fractions of Eulerian polynomials at q to the mj divided by 1 minus q to the mj to the power kj. And if we multiply this by 1 minus q to the weight, then each of these gets a factor 1 minus q to the power k. So if I multiply this and put it in here, then I will always have here the q integer of m1 up to the q integer of mr, and sending q to 1, and together with some argument y I can put in the limit inside the sum, we can show that for an admissible index k, the limit goes to the multiple zeta value zeta k. So in other words, these are modified q-analogues for multiple zeta values, but they are defined for more indices. So multiple zeta values are just defined for admissible indices, and these are actually defined for all indices. So for all indices, they give some formal Q series with rational coefficients. And these guys we now want to study. So we define the space spanned by these by G. So this is the Q vector space spanned by all these Q series for all indices, not just admissible but also non-admissible. And this is the subspace of the space of the ring of all Q series. And we will now see that this space is also closed under multiplication. Well, we will see this in the smallest F's case, and in the next section we will make this precise and show that this space is actually closed under multiplication. And to do this, so let's try to do the smallest case. So if I multiply G, so let's say k1 and k2 are greater or equal to 1, and I multiply G of k1 with G of k2, this, well, by definition, I take the sum here of the Eulerian polynomials at q to the m1 divided by 1 minus q to the m1 to the power k1, and this is also a k1, times m2, so Eulerian polynomial k2 evaluated at q to the m2, 1 minus q m2 k2. And now the usual game, we just consider the three cases. m1 is greater m2, m2 is greater m1, and they are the same. But the first of these, so if m1 is greater than m2 and I take the sum over these two, then this is just the definition of these G in depth 2. So the m1 is greater than m2 case, this just gives G of k1, k2, plus in the case m2 is greater than m1 gives G k2, k1, plus, and now if they are the same and they are both m, we need to consider this product here. Q to the m, k1, pk2, qm, 1 minus qm, k2. And to show that this is again an element in this space, we need to argue why this sum here can be written as a linear combination of these small g. And since this is a single sum, it would be enough to show that this product here of these two rational functions is again linear combination of a rational function like this. And this is one of the exercises, namely, you show that the following lemma holds. So, oops. So we give these two guys a new name, just to write less. So this is rk1 of q to the m, and this is rk2 q to the m. And you can show that if you take a product of two of these rk of x, I mean, here now it doesn't matter what we put in there, which is defined exactly by this rational function here, or which was defined by this, then one can show that the product of two of them is given as, we can first write this as R of k1 plus k2, and then a linear combination of rj's for j being strictly smaller than k1 plus k2 with some rational coefficients. And these rational coefficients can be written down explicitly, given by some binomial coefficients and Bernoulli numbers. So if you plug this formula in here, then you can see that since there's still the sum here, that this will give a linear combination of small g's. So more precisely, what we will have is this formula here. So this part we saw above, and then using the lemma for the remaining part gives this part here. And so the product of these small g's is quite similar to the product of a Riemann zeta value, but we also get some lower weight. Well, we didn't define what we mean by weight, but by weight we mean the sum of the case. And here this gj are of smaller weight than the sum k1 plus k2. And further, if I multiply this, the whole thing here, if I multiply by 1 minus q to the weight k1 plus k2 and send q to 1, not to 0, to 1, then clearly this vanishes, because I know that if I multiply this by 1 minus q to the weight j and set q to 1, this gives zeta j. But since this j is smaller, I still have some factor left, 1 minus q, and if I send q to 1, this goes to 0. So this vanishes, and this here will give exactly this Stafford product of multiple zeta values. Okay. So this is the first product analog. So we have an analog for the Stafford product of multiple zeta, of single zeta values. But we also have an analog for the shuffle product. So the shuffle product of multiple zeta values was, or of two Riemann zeta values, was given by this formula here. So we just had a linear combination of double zeta values. And now we have a formula for these small g's. And here the case are allowed to be greater or equal to 1. And the first, so the def2 part is exactly the same, like in the multi-zeta case, plus, and now something new comes into the game. So we still have something of lower weight, but now we also have the derivative of this q series with respect to this operator q ddq. And this q ddq, if this q is e to the 2 pi I tau, usually is basically just corresponds to the derivative with respect to tau up to some factor 2 pi I. And this is, so therefore this is a quite natural operator in this theory, because modular forms are holomorphic functions in a variable tau. So you can ask for the derivative, and on the level of q series this derivative is exactly given by this q ddq. So here we see that, so this product, we can ask, is this again an element? Well, we know this is an element in G because we had the other formula before, but from this expression it's not really clear because we have this derivative here. But you can also now view it the other way around. So we can use the product we saw before, this one here, to evaluate this. So we know this is an element in G. The rest is an element in G. And therefore also the derivative in this case needs to be an element in G. And this we will see later, that this space G, where is it? Ah, there it is. So later we will see that this space is actually closed under this operator ddq. And this proposition we see here is somehow gives the proof for the together with the other proposition, gives the proof for the smallest depth version. Okay. So now let's do some examples. So for the multiple zeta values, we did some examples for this stuffle and shuffle. So if we multiply zeta 2 with zeta 3, then the stuffle product gives this, and the shuffle product gives this. And then we had a linear relation here called these finite double shuffle relations. And using these two propositions, we can evaluate these products. So here's this stuffle product, where here we have this extra term coming from these here. So here, remember, the lambdas are basically just some binomial coefficients and Bernoulli numbers. So here we get this in this case, and the shuffle product formula, this part here, in the case 2 and 3, gives the same as the shuffle product of multi-zetas. So this is this part here. But then we also have the lower weight term here, and we also have the derivative, in this case, of G3. And also, what I forgot to mention is that if I take this formula here, we also get back this formula by multiplying by 1 minus q to the k1 plus k2 and sending q to 1. So one needs to, so the only open thing is to show that this actually vanishes under this limit. And another example, so because these formulas also work for non-admissible indices, we can also take the product of G1 with G2. So the stuffle product formula gives this, and the shuffle product formula gives this. So therefore we get the linear relation that G3 equals G21 plus some derivative of G1 and some multiple of G2. And this is actually, if one sends q to 1 here, so multiply by 1 minus q cube and send q to 1, then we get back this relation zeta 3 equals zeta to 1, which for multiple zeta values we didn't prove by using double shuffle, because this doesn't make sense for multiple zeta values because we cannot multiply with zeta 1. But in this setup here, we can prove this by using these double shuffle relations. But we will also see later that we can extend these double shuffle relations for multiple zeta values, and then we can basically do exactly the same. But here in this Q world, we don't need to worry about zeta 1, because G1 is a well-defined object in our space. Okay, so now I didn't say how to prove this thing here. So in the first one, the stuffle product formula, I indicated how to prove it by proving this lemma in the exercises. But to prove this, I now want to explain why it's nice to use a generating series in this setup here. And we will also see that actually this formula here, the stuffle product, will also follow from this if we consider a generating series. Okay, so the generating series of these small g's, which are defined for all k's, so generating series just means I take the sum of all of my objects and write them in front of some coefficients of some variables here. So this makes sense for all r greater or equal to 1. And we denote this series here as German g of x1 to xr. And the nice thing about the small g is that these generating series have really simple explicit expressions, and there are two ways to write them. And using these two ways will give, using the one way, we will get the stuffle product formula, and using the other one, we will get the shuffle product formula. So let's do this, or let me try this in depth 1. So what is Okay, so now I'm sorry. So this is German G of x. So this is a generating series of small g x k minus 1. So let's write down the definition. This is the sum m of the Eulerian polynomial at qm 1 minus qm k x k minus 1, and this is should I write it here? No, I will write it here. So this is the sum k greater equal to 1, m greater equal to 1, and the definition of Eulerian polynomials was I have a sum over d greater equal to 1, d to the k minus 1 factorial, and now I have q to the md. So in the definition I had pk of x equals, and here I have x, but now I plug in q to the m times x to the k minus 1. And now there are two ways to evaluate this sum explicitly. So, and the first one is I can sum over k first and then over d. So if I sum here over k first, what do I see here? What depends on k? So this is basically just the exponential function where I plug in d. So the m sum is still there, the d sum is still there, and then I have exponential where I plug in dx, and then I still have this q md. And if I take the sum over d now, I have the sum m, and then this is just a geometric series here. So this is e to the x times q to the m divided by 1 minus e to the x q to the m. So this is one way, one explicit formula for the generating series gx. So the other one is that I sum over m and k. So if I sum over m first, I still have the sum over k. I still have the sum over d. And where is m here? So m is just there, so I just have a geometric series. So I still have this guy there, x to the k minus 1. And here I have now q to the d divided by 1 minus q to the d. And now taking the sum over k, which I have here, this is just, well, I could also take first the sum over k and then the other way, but so I have d is greater equal to 1, and here I have e to the dx q to the d 1 minus q to the d. So this is another way to write the generating series of this g in the case r equals 1. And the general lemma is this one. So let's compare this to what we did. So in general, this generating series g has two expressions. So this one here corresponds in the r equals 1 case to this one here. And this one here, in the case r equals 1, is exactly what we have here, except that we renamed this d to m to get this sum here. And using this idea in general, you can show that you have these two expressions, where in the second one you need to work a little bit, because a priori you will have different d's here which are not ordered, and then you will change these D to be ordered, and this is why you will get these minus signs here. And this is one of the exercises to do, but this is maybe the main idea to prove this. And now, so this is somehow the Staffel version of the generating series, and this is the shuffle version. And what I mean by this is that we will now use this expression to prove the Staffel product, and we will use this expression to use the shuffle product. And this we will do now by giving explicit formulas for the product of two of these generating series in the case r equals 1. So this is this proposition here, namely the product of two of these generating series can be written in two ways. One way is exactly this, which will give the Staffel product formula, and the other way is that we can write it like this. So here we have just the generating series of these g with some variable change, and here we have the derivative with respect to this operator q ddq, and here it's somehow a shift of this generating series of this small g, and then also we have a constant term here. So this guy here will later explain why we have this factor here, where I forgot to say that these are the Kronecker delta. So delta ij is 1 if I equals j, and 0 if I is not equal to j. So this factor here just appears when k1 and k2 are both 1. So if we take this product here of g1 times g1, then we have this extra factor of g2 here. And so the proof of the proposition before is by considering the coefficient of x to the k1 minus 1 and y to the k2 minus 1 in this equation here, and this will give this formula here, and considering the coefficient of this in this expression here will give the Staffel product formula given here. Okay, so let's sketch the proof of this expression here, and what I just said is actually also exercised to show that this proposition here actually implies these two functions. So one needs to work a little bit on this term and on this term here to see that you actually get these explicit formulas you saw before. So let's try to understand why we have this here. So let me write this down. And again, so the key idea is now to use this lemma here. Maybe I can put it here. So now, to prove this one, we will use the first formula. So here I will now use that this is e to the m1 x q to the m1 1 minus e to the m1 x. Oh, sorry. This is just x. Yes, so this is exactly what we calculated here. Times m2 e to the y q to the m2 1 minus, oh, here's also m1 e y q to the m2, and then it's again the game that we consider the case m1 is greater m2 greater 0, m2 is greater m1 greater 0. So these two are exactly just this here. because here we see that this is just this formula here. So if I take an ordered sum of the product of these two, I will just get exactly this g in depth 2. But the interesting part is when they are both the same. So I have e to the x qm 1 minus e to the x qm times e to the x times not e to the x e to the y qm 1 minus e to the y qm. And now we need to evaluate this thing here, and you can check by direct calculation that you have this following here, that this product, which is exactly this here, can be written as this first term multiplied by this function here, plus the second term here multiplied by this. And since we have the sum over m here, and the sum over m of these are just these generating series in depth 1, we see that that these factors are exactly these here. And also notice that, which is part of this exercise, that this function here has actually a pole in the case x equals y, but here we also have the same one here. So you need to rewrite parts of this, so you get 1 over x minus y times gx from this plus something, and from this you get 1 over y minus x, or in other words you get minus so in other words you get minus 1 over x minus y gy plus something without terms, without poles. So, and then you need to see that this term here actually doesn't have a pole in the case x equals y, and you need to evaluate this and consider what is the coefficient of this in this sum, what's the coefficient of this monomial in this series here, and you will find out that this exactly gives this part here, this k1 plus k2 part, and the remaining things without poles will give these fancy lambdas. And the reason why Bernoulli numbers come into the game is that this looks similar to the generating series of Bernoulli numbers. Yes, and homework is to work out this precisely. Okay, so now the second formula, this one here, how to evaluate this. So here we will now use the second expression here, which I called here the shuffle expression. And here I just recall what this expression looks like. So let's write this down in the case r equals 2. So what is this formula saying in the case r equals 2? So it's an ordered sum, m1 is greater than m2. And here I now have e m1 of xr. So r is 2, so this is x, this is y, q to the m1, m1. Maybe let's call this x1 and x2. Then this here is x2. And then I have e to the m2 times, and the last part is always x1 minus x2. x1 minus x2. q to the m2. 1 minus q to the m2. Okay, so now let's see what happens if we multiply gx with gy. So again, this is using this expression in the case r equals 1 gives m1 x q to the m1 divided by 1 minus q to the m1, and this gives m2 is greater than 0 to the m2 y q to the m2 1 minus q to the m2. And again, so now what will we get by m1 greater than m2 greater 0? Well, this is now just not just the g in depth 2, because we have something like this. But if you compare this now with the depth 2 g, then you see that this is exactly g of x1, g of x plus y, comma x. Because this one here is always the second entry, so the second entry is x, which is here, and this entry is the first minus the second. So here the first minus the second is just y, so that's how we get the y here. And also, if you do the same for the case m2 is greater than m1, then you get g of x plus y, comma y, because in this case we have a y here and an x here, plus, and now we get the case when they are equal, and this in this case is e to the m x plus y, and now q to the m squared. So we need to evaluate this guy here, and so this is what we have now. The product of two of these g's is this g in depth 2 with this change of variables and this, and then we have this term here, which we now want to write in terms of these generating series. And this, so I put them here, can be done in the following ways, which is also part of the homework. So first, this part here, you can check that this is just q to the m divided by 1 minus q to the m squared minus q to the m over 1 minus q to the m. Because if you multiply this by 1 minus q to the m, and then you will get this. Therefore this one here, which is just this, can be written as the sum with this factor here, minus this one. But if I put this here, then this is just the generating series of small g in depth 1 with the change of variables where I evaluate this at x plus y. And the first part here will give this sum, and the exercise is to show that this can be written as this series here. And to do this, you should just consider, for example, if you take the derivative here, you will erase this k here. For example, if you take the derivative with respect to y, and here if you take the derivative with respect to y, you get some m coming down here, and you will see that if you multiply something like this with some m, this will basically correspond to some derivative of this g. Okay. So this, if we use this formula for this part here and put it in here and also have this extra term there, we get in the end this this explicit expression for the product of these small g's, and then considering these coefficients we get this shuffle product formula we saw here. Okay, and so these small g's are one example of so-called modified q-analogues of multiple zeta waves, and they are inspired by these Eisenstein series by just making a multiple version of this tail of the Fourier expansion of Eisenstein series. But instead of taking these Eulerian polynomials in the numerator, we could also just take another polynomial, and also a lot of models of q-analogues in the literature are of this shape. So what we want to define now is a more general class of generalized of modified q-analogues, and one reason is that the shuffle product we saw, for example, here involves some derivative, and in higher depths, if we multiply some g of depths r1 and some g of depths r2, we will see that not just derivatives will appear in the shuffle product, but also some new objects which somehow can be seen as partial derivatives in some sense. And therefore, to describe the product, this shuffle product analog, we will need to extend our space to a bigger space in which we can describe this shuffle product quite nicely. And this space I want to introduce now. So I want to call this a general modified q-analogues of multiple zeta values. And what I mean by this is that for some index k1 to kr, and now some polynomials q1 up to qr, where q1 needs to be 0 at 0, we define now this q series zeta q depending on these numbers k1 to kr and these polynomials q1 to qr by this sum here. So maybe let's, so for example, these series g we saw before, k1, kr, they were just given by zeta q, k1, kr, where we choose here the Eulerian polynomials. And they satisfied this condition here, because in the homework you show that pk of x is, pk of 0 is 0, so it satisfies this. And the reason for this condition here is that what I mentioned at the beginning, that this first polynomial here shouldn't have a constant term, because otherwise this wouldn't be a well-defined q series. So this is again a q series. And also this Bradley-Chow model we did at the beginning, so which I denoted by Bradley-Chow, k1 to kr. So this was not a modified q-analog, it was a q-analog. So, but if we erase this factor, so minus k1 up to minus kr, then this is just this zeta q, k1 up to kr, and the polynomials used are just the polynomials x to the k1 minus 1 up to x to the kr minus 1. And here it's important that this k1 is greater or equal to 2, at least for this part here, because here we see if k1 would be 1, then this would have a constant term, and this object doesn't make sense. And then the space we introduce is the following, zq, which is now the q vector space spanned by all these by these generalized modified q-analogues, where we also have, we restrict to the cases where the degrees of these polynomials are smaller or equal to k. So in these two examples, these polynomials were always of degree kj minus 1, except when these k's are 1, then they are of degree 1. And so this here shows that this space G is a subspace of this ZQ, and also this ZQ is also, it's easy to see that this is also closed under multiplication, because if I, for example, multiply zeta k1 of q1 with k2, q2, then this is just zeta k1, k2, q1, q2, plus zeta q, k2, k1, q2, q1, plus, and if the m's are the same, then I just multiply these q's here. Oops, I don't want a sum here, I want zeta q, k1 plus k2, So I add the indices and I multiply the polynomials. Yes, and this space we will consider in section 5, and we will show that on this space we can define the shuffle product in a nice way. So in the next section we will see that this shuffle product is an example of a so-called quasi-shuffle product on the space G, and for this space ZQ we can define some involution and then can define a new product which combines this involution and this quasi-shuffle product, and then which will correspond then in the end in some magic way to the shuffle product. And one last remark here is, so clearly this G is a subspace of this ZQ, which is a really big space, but conjecturally we expect that these two spaces are actually the same. And this is based on numerical evidence and is proven up to weight, so proven for weight smaller equal to 8. But numerical experiments indicate that this is true for all weights up to, actually I forgot the exact number, but for higher weights than weight 8. And this is quite surprising, but this also means that there might be a way to explain this shuffle product purely on the space G. And at the end of this course maybe we can give some motivation why this conjecture might be of interest. And the short version of this is that a lot of Q-series coming from other fields, for example some counting problems in geometry, they produce q-analogues, they produce Q-series which a priori lie in this space here, and there people are also interested in the limit q goes to 1. So if this conjecture would be true, then all these examples would lead to limits which live in the space of multiple zeta values, because this space G always reproduces multiple zeta values when taking the limit q goes to 1. Okay, but this we will do in section 5 here, where we'll also consider this operator q ddq and show that this space G is closed under this operator q ddq. And we will also see that these small g appear in the Fourier expansion of so-called multiple Eisenstein series. But next time we start with section 2 and talk about iterated integral expression and multiple polylogarithms. See you then.